proof of work chain built by miners. So, if Alice can just give the signed transaction to Bob to transfer coin, and Bob can just pass it on to Carol, well, why do we need miners in the first place? And the reason is only to prevent one of those people in that chain from spending the same coin twice. For instance, if Bob received that transaction from Alice, he can see that it's valid, but he doesn't know whether Alice maybe signed that same coin over to someone else. So the reason we need the miners is just to prevent anybody from spending the same coin twice. Okay, so earlier I described how the miners, they package up the transactions they want to confirm, and they write the digital fingerprint of that set of transactions in that root hash square. But the way they calculate that root hash is the real magic that allows Bitcoin to scale to billions of users. So what the miners do is they first hash all of the transactions they want to confirm. And then they hash the hashes in a pattern like this. Then they hash the hash of the hashes and repeat that until they get down to a single hash called the root hash, and the rest is the hash tree. So this is brilliant because it allows the miners to prove to Bob that his transaction was included in the blockchain in a very compact way. All they need to do is provide Bob with these two pieces of information shown in orange. Bob already has the transaction. That's what he received from Alice. He can calculate hash 3 himself. With hash 2 that he received from the miners, he can calculate hash 2-3. And with this hash and that one, he can calculate the root hash. And if the root hash he calculates independently is the same as the root hash in that chain of headers that Bob's wallet is tracking, then that's cryptographic proof that the transaction that Alice gave Bob has been confirmed in the blockchain. So this isn't too impressive when you look at it with only 4 transactions in a block, but the way this scales is really cool. So if there were 8 transactions in the block, that would add 1 layer to our tree, and Bob would require 3 pieces of information from the miners. 16 transactions in the block, Bob requires 4 pieces of information from the miners. 1,000 transactions in the block, Bob requires 10 pieces of information, or 320 bytes. 1,000,000, 640 bytes. Even if there were 1 billion transactions in a block, Bob would only require about 960 bytes of information to prove to himself that the transaction was confirmed, which really isn't a lot of information, but 1 billion transactions in a block is probably bigger than Bitcoin will ever grow to become. Okay, so are there scaling challenges with respect to proving inclusion in a block? The answer is no. SPV technology works. It's easy for users' wallets to track the proof of work chain. It's easy for users to send and receive transactions. And it's easy for miners to prove to users that a transaction was confirmed in a block. So before I gave this talk, I asked on social media, what needs fixing with SPV? And one piece of feedback I got is that people just don't realize how secure SPV is. They think you're trusting nodes, or they think that they can be defrauded. But SPV is highly secure, and as far as I know, there's not a single example of someone using an SPV wallet being defrauded in a case where they wouldn't have been defrauded if they were using a full validated node. The other piece of feedback I got was some people are concerned with SPV privacy, and I think there's some legitimacy to that concern. So, to understand what the privacy concern is, ask yourself the question, how does Bob get that information he needs from the miners to prove to himself that his transaction is confirmed in the blockchain? I showed you this picture, and I said that Bob needs those two pieces of orange information there. Well, basically, he needs to ask one of the miners, or he needs to ask one of the network nodes for those two pieces of information. But to do that, he has to reveal the transaction that he's looking for the information for. And if he's always asking the same node or the same miner for that information, well, that node can correlate his transactions with Bob's IP address. And that information is valuable for data miners and potentially dangerous for Bob if people can see all the ways he's getting money and all the ways he's spending his money. So one improvement is that SPV wallet should simply connect to more nodes. Concern number 2. So the Bitcoin developers have tried to improve SPV privacy in more sophisticated ways as well. BIP37 is a technique based on loop filters that basically allows an SPV wallet to say to a node, give me all the proofs for transactions that get caught by this filter. And this filter is a filter which is designed to catch all of the transactions that Bob cares about, but a bunch of other transactions that Bob doesn't care about as well. So the purpose is just to confuse the nodes so they don't really know which of those transactions are Bob's and which are just random transactions. You can already see that there's this bandwidth versus privacy trade-off emerging. So we've increased Bob's privacy, but we required him to download more information from the nodes. We've increased his bandwidth costs. Okay, so Brad Wallet is an example of an SPV wallet that uses BIP37. BIP 157.158 is designed to improve upon BIP37, and it's kind of the opposite of BIP37 in a way. Instead of the node saying, instead of the wallet saying to the node, give me all the transactions that match this pattern, what BIP 157 does is the nodes of the miners themselves, they calculate this compact filter that represents all of the transactions in all the different blocks. So Bob's wallet can download very easily that compact filter and then test whether any of the transactions that he's looking for are included in the block in question. If they are, then Bob can download that entire block from some other node. And this way he leaks no information about his wallet or the transactions he's interested in at all. But we've increased Bob's bandwidth requirements even more because now he's downloading full blocks once in a while, which becomes infeasible if we imagine a future with gigabyte plus blocks. So again, we see this bandwidth privacy trade-off. And Neutrino is a SPV wallet that uses BIP 157.158. Okay, so improvement number 2, I think we need to better understand this bandwidth versus privacy trade-off. Concern number 3, how does Bob actually receive his transactions? So I showed you this diagram. I said, Alice signs the transaction, packages it up, and delivers it to Bob. But it normally doesn't happen that way. Normal wallets, like even if I wanted to send a payment to Jason, who's standing right over there, if I send him a payment with my wallet, it's not going to just deliver that transaction to Jason. It's actually going to send it into the Bitcoin network. It's going to get relayed all around the world, and then Jason's going to download it on his wallet. So how does Jason actually see that transaction? Well, one way is just for Jason's wallet to be listening to all the transactions everywhere. But if you imagine a future with 100,000 transactions per second, that's not really feasible from a smartphone. So what most wallets do today instead is Jason's wallet would add all his addresses in his wallet to that loop filter from BIP37. And now when the nodes that Jason's wallet is connected to see a transaction related to Jason's wallet, they're going to forward it on to him. So Jason can get the transactions he is interested in without seeing all of the other transactions in the world. But here again, we have this huge privacy leak because all of your addresses are being sent to the Bitcoin network all the time. So you're leaking address information. So improvement number 3 is wallet developers need to directly deliver the transactions to the payee whenever possible. We need to stop relying on the P2P network to deliver the transactions for us, because it's a privacy leak. Last point, concern number 4 is just all the addresses we have in our wallets. You can imagine you're using your wallet, you've maybe generated 100 or 200 addresses over the lifetime of your wallet, and you've given those addresses out to all sorts of different people, and you never really know when someone's going to pay one of your old addresses. So the way most SPV wallets work today is they're constantly checking for payments coming in on all 100 or 200 of their previous addresses. Again, this is a privacy leak because they have to be exposing and sending out the addresses they're interested in to the network all the time. So you're constantly leaking information about your addresses into the network. What we need to do is really move away from addresses as something that's visible to the user in the first place. We need to make addresses truly single use, and they should be completely invisible to the user. And this will significantly improve privacy. And that's all I have to say. I hope I've got you excited about what we can do with SPV in terms of scaling. Thank you for listening.
Whoa.